Welcome back. So now we're going to pursue our second vignette having to do with the great probability distributions. And as I indicated at the beginning, the way that I wanted to structure this was by virtue of appealing to different case studies. So you'll recall in the last vignette, which led us to the binomial distribution, that the question of interest had to do with the way that molecules partition during cell division. And our null hypothesis, between quotes, was that the molecules or the carboxysomes or the transcription factor or whatever it is that's being segregated during cell division, that they effectively flip a coin and they go either left or right based upon whether or not they get a heads or a tails. And we found that in the case of the carboxysome, that hypothesis was found wanting. In other words, the statistics of that null hypothesis were not consistent with the measurements. So here, the pursuit today is, in this particular vignette, is one version of the exponential distribution. And more specifically, we're going to address a puzzle, which is the so-called waiting time distributions. And what I have in mind here is that we have some situations such as the dynamics of an ion channel, and this is open, and this down here is closed. And now I'm going to imagine that, this thing is doing something like this. Maybe getting kind of lazy, but something like this. Okay, and so you get the idea, which is that this is an open state of the channel, and this region is closed state. And the way I might represent that is to say that here, I have some ion channel, and it's open in this situation, and then in the closed case, which I'm going to put over here, no, it's closed. So this is the closed state. Okay, so the channel is fluctuating back and forth between closed and open. And just as an aside, we might be interested in writing P open, the probability of being open, and that would be the sum over, n equals 1 to capital N, the time that it's open when it's in the nth open state, and then I divide that by T tot. So what is this idea? It's saying if I want to figure out the probability of being open, then what I want to find out is what fraction of the time does it spend open. So that's a statistical question that we will later answer using methods of statistical mechanics. The other point that we can consider is we can consider the time spent closed. So the idea here is that I would watch the system, and I would measure how long it takes when it's in the closed state, and then I would histogram. And I would basically make a histogram of the time spent in the closed state. And the thing I'm going to ask right now is what kind of hypothesis might I be able to write for this process? So the way I'm going to represent this is through a kinetic scheme. And the kinetic scheme is going to be characterized by two rate constants. So K plus is the rate constant for transitioning from closed to open. And similarly, K minus is the rate constant that we will use for describing the transition from open to closed. Now, you might remember that earlier in the term, I suggested this new way of thinking about the nature of these rate constants. So I'm going to ask you to recall that k plus delta t is the probability in a small time interval delta t of making the transition from closed to open. Okay, that's really deep. I'm not saying I'm saying anything deep. I'm saying that people that figured out how to think about these problems had a deep realization. So now we're in a position. So our goal is to compute the probability of surviving in the closed state until the interval between capital T and capital T plus delta T. Okay, so what do I have in mind here? I'm saying that and also T tot is equal to n times delta T. In other words, we're asking that the system survive in the closed state for n time steps, and then on the n plus 1th time step, it will transition to the open state. Okay? Or alternatively, we're in the open state and we transition to the closed state. It doesn't matter which order we think about that. Now, let me try to give you a little bit of a sense of how this works, like the logic of how we're going to construct that probability. So the thing that I want to call your attention to, here I'm showing ligand receptor binding, but the mathematics is exactly the same, whether it's this or ion channel opening or the stepping of a molecular motor. All of those are going to be described by the same basic kinetic scheme, which is every instant, either the system stays quiescent, it does nothing, or it makes the transition. And what I'm trying to highlight here is that the probability of making the transition is given by this. It's k off times delta t. In this case, I'm talking about a ligand falling off the receptor. So the probability of that happening in a time delta t is k off delta t. The probability of that not happening is 1 minus the probability of it happening. There's only two things that can happen. Either it stays put or it comes off. So if it doesn't come off, then it stays put. So that's 1 minus the probability that it comes off. So now what we want to do in order to compute the probability of surviving n time steps is we want to string together a series, as you can see here, a series of quote-unquote successes where nothing happens, and it's going to do that n times. So we want to construct, so the probability of transitioning at a time between t and t plus delta t is going to be given by 1 minus k off delta t. This is time instant 1. So in the first instant, we want to survive without a transition. Then in the next instant, we want to transition. We want to survive, no transition. So this is time instant number 2. And we're going to do this n times. So we basically want to survive n times. So we have n of these. And then in the last instant, we want to fall off. So in the very last instant, this is the probability of a success, of falling off. So the total probability of surviving until the instant between t, capital T, and t plus delta t is we string together n failures, if you'll let me call it that, and then on that final instant we have a success. So I can rewrite this as 1 minus k off times delta t to the capital N power, and then k off delta t. But I also note that I can rewrite this as 1 minus k off, and then t divided by a capital N to the n power k off delta t. Why? Because t is n times delta t, which implies that delta t is capital T over n. Okay, I've simply used that correspondence. Now, what's interesting, and I'm not going to go off on the tangent too much, but this is, you might recognize this if you check your memory banks. You might recognize this as something that you saw in some early class in which somebody forced you to do something about compound interest. And I basically want to show you here the idea. So what we're going to do is a little exercise in experimental mathematics. So what I'm going to do is I'm going to evaluate this expression. Why? Because that's basically of the thing we're looking at is of the form the n power, and so modulo that minus sign. By knowing how to handle this thing over here, I'm going to invite myself to know how to handle the slightly more complicated case shown over there. So here's the scheme. We're interested in a large n. In other words, we want to see probability of surviving a long time compared to our little itty-bitty time step. And all I'm asking you to do is we're gonna choose different values of capital N, and then on the right-hand side we're going to calculate 1 plus 1 over n, all raised to the n power. So if I choose n equals 10, I find that that's equal to 2.5937. If I choose 10,000, then I get 2.7181, and if I choose 100,000, I get 2.7183. And so what's plotted on the right-hand side actually is e, so e to the first power, that's the blue line. And then the red line is our expression, 1 plus 1 over n to the n power. So what we've learned is that the limit, as n goes to infinity, of 1 plus 1 over n to the n power is e. And I can now tackle the case of 1 plus x over n to the n power by defining 1 over m is equal to x over n, or m is equal to n over x. So that means that n is equal to mx. So I can rewrite this thing as 1 plus 1 over m, all to the m power, and then to the x power. And that's e to the x. So what we've learned is that this expression up here, I can now rewrite this as e to the minus k off t, and then times k off delta t. This thing is our probability density, p of t, which is the probability density for surviving until t and t plus delta t. In other words, this little interval. So what we found is that this is an exponentially decaying function. In other words, what we've said is that the probability of a waiting time, capital T, is e to the minus k off times capital T multiplied by k off delta t. So this is a really deep and profound result, because what we've said is that we have an exponential waiting time distribution. And I will leave this here for the moment, but in a homework you'll have a chance to sort of repeat this derivation to explore the nuance of this idea of a probability density versus a probability. P of t has units. But we know that probabilities don't have units, so that's the reason that there's this delta t. So the P of t delta t has no units, it's a probability.